Waves, good. Okay. So we moved away from a discussion of just thinking abstractly about all the ways in which maybe we can create momentum, create energy. And now we're going to think about how the fluid actually moves under those constraints, right? And so in order to do that, we were talking about, oh, fuck my life. Here we go. Okay. We were talking about linear liquid surface gravity waves, something like this, right? Recall this? And we had essentially got into something that looked like they have an eta, right? What was eta again? As a word? Eta is the free surface. Okay. And what you're going to be measuring here is you want to understand how it changes with respect to time and space. And we wrote something essentially like this: d phi dt plus the pressure divided by the density plus g times z equals 0. We said that this was from the Bernoulli equation. You recall that? So there's an interplay here between this thing d phi dt, something like the pressure forces, something like the gravitational forces, right? And what was d phi dt? Phi by itself. Yeah, what is phi? That's what? You're saying the word potential, and I like that, but I can't hear the word in front of it. Oh, the change. So if I were to write W, right, this comes from W equals d phi d z, very good, right? And if I wanted to write U, that comes from d phi years, right? So what we're saying here is that phi is a scalar potential. Q equals the divergence, right? Not the divergence, not the gradient. Something like that. That's how we wrote our idea of a stream function. Velocity potential. Is that fair? So what we're asking is, how does the velocity potential change with time? And that can only be due to pressure and gravity. Pressure can push the velocity, or gravity can pull the velocity. Right? Okay. Now we're Gucci. So we can then evaluate this at the free surface, this location here. So we choose a place for z equals eta, okay? And we can apply this here such that we can take this whole thing. And let's see how we're going to write this out. I guess the easiest way to write that out. This is going to look reductive, but it's fine. Okay. Plus e rho plus G Z evaluated at Z equals eta, okay, is approximately equal to phi t plus G eta. Approximately equal to 0, right? Here. Is that okay what I said? But when I think about Z equals eta, which is right here on the free surface, okay, I evaluate that. What does this middle term go away? Okay. Z equals, no, this one right here. What does that go?
The pressure of the surface is so minuscule, right?
Very close. It's not minuscule, it's 0. Remember, we said that it was. We said that by definition, the boundary condition at the surface, at the free surface, is 0. That's what defines the free surface. It's the place where the pressure disappears. Because you have a fluid down here and something else up here. Right? If we brought this thing down into here, it would not be a free surface. It would just be a layer in the water. There would be pressure, right? So down here, the highest pressure, as I go up, it goes to 0, and then it can't go lower. So by definition, the free surface is the location at which P equals 0. So when I evaluate this, rho, Z at eta, this term must be 0, right? So while this is true everywhere in the fluid, at the boundary, it's really just these two, right? And more importantly, at the free surface, I can rearrange this so that d phi dt is equal to minus J eta, right? Okay. Okay, so now let's be really smart. Let's be clever. Be smarty things. We love some good math, right? Do we? We love derivatives in this class?
Yes.
Yes, we love derivatives. Let's fucking go derivatives. Okay, so we've gone a long ways. Okay, we've got a lot of shit, and we have some other shit that we need to work on. In particular, let's think about this earlier statement. Let's think about this earlier statement about Laplace equations. Okay, I kind of set it up here earlier. We had something like the velocity potential, right? And that was this thing. Fine. Okay, but I also should have alluded to the fact that you have something like this. Del squared of phi is 0. We said that? Okay. We have some boundary conditions like d phi dz at the boundary is 0, right? So let's make a guess. Let's assume that psi has a certain form, or phi has a certain form. So let's say phi is going to be a function of x, z, and t. Okay? We're studying waves here. So what should we guess the solution to be? Yeah, let's do a sine and cosine, right? So let's think about a sine or cosine. I'm going to have it be sine of what? So eta is the location of the free surface. So eta already is a function. We want to write what phi might be, and that will give us a version of eta by this relationship. We're getting there eventually, right? Something with time, right? So if I have time, then I need
Speed, so.
Would it be the scalar potential? Or is that well?
no, so if I have inside of a sinusoid, okay, inside of any trigonometric function, the interior must have no units. So if I have a time, I need a omega, a frequency. Okay, so let's do omega k, or sorry, omega t. Now omega here, I'm going to point out, is going to be a function of k. So we'll see what that is in a second. Okay, and then the next one,
The KX.
kx, right? Okay, kx minus omega t. That's a pretty standard formula, right? We kind of mix together whether the wave is going up and down and whether it's traveling left and right, right? How does it change with respect to x? Up and down. And then finally, we're going to throw onto it some function f of z. Okay? So we're going to.
The amplitude,
What?
that should be a like amplitude.
Yeah, that absolutely would be a. But I'm making it strictly a function of z. And you're going to see why. Remember, this is a 2D problem. You have a function in f, I'm sorry, function. You have a z and x only, there's no y. And what we're doing right now is we're saying to ourselves, this is a mathematical technique. I know that this thing depends on x, z, and t. I will guess that it is separable. Okay, this is separation of these two variables, one component multiplying the other. Because when I look at something like this that I want to solve, then I'm going to have one version times the derivative of the other, plus one version times the derivative of the other. And if they equal 0, then I can divide both sides by the original function, and I'll get something with respect to x and something with respect to z, and they'll be completely separated. Okay, so this is a technique that we like to use. So let's try it. Okay, let's put this thing into Laplace's equation. So that's Laplace's equation up there, right? What's the first part of Laplace's equation? It's something like this: d squared dx squared of phi plus d squared dz squared of phi equals, well, now let's put what phi is. Okay, so for the first part, I get f of z, that comes out, and I have two derivatives of sine. I'm not going to write the interior. Plus, what's the second part? Sine is in the front, right? And then it's two derivatives with respect to z of f, right? Of z. And all that equals 0. Now, do we know how to take a derivative with respect to x? Of that function? Of phi? Yeah, k cosine. And what's two derivatives?
B squared sine.
Good. So this thing here is just minus a squared sine. Okay. So now I have sine in both terms and I have 0 on the other side. So those are gone. So I can say here minus k squared f of z plus del squared del z squared f of z equals 0. Look at witchcraft. Any X's? Any T's? No, isn't this magical? Okay. So what's the answer? What's f of z? Let me rewrite it. You need that. You need it rewritten or you like it?
Get rid of the sign.
Sine. Cancel. It's not in the K. The K is the K. Right? This one here?
Yeah.
This actually doesn't have a number yet. But you will see it very shortly. It will become 823. But this is a format you should know and love. Okay, d squared f dz squared equals k squared f. You see this, you should immediately say blank. Faster. Oh, close, you're almost there. E. Why is it E? And not sine? Why did I say no so emphatically? You already did it. You did it right here. What happens when you take two derivatives of sine? You get what? What did you get here? It was positive. So that's the way you can tell the difference between the exponential and the sine, right? So you say to yourself, okay, I got two things. So I took the derivative twice, I got k, and then I got f. So now this tells me that f can be E. Good. Yeah, that would be funny if it wasn't, right? Got it, nailed it. What?
K squared is multiplied by that.
Yeah. Okay, it's k squared f. Right? A z needs to be in there?
It has to be a function of z.
Good. That's it, right? Why do you add a t? There's no t's. So there's nothing to do with t. F of z, remember, is f of z. T is over here. T's in the sign. We'll deal with the t later. Okay, so what's this one? Exponential is? Nope, not just z. Good. So there is a z, but there's a where'd that come from?
Here's one K, also here's one K.
Yeah. Right? Is that true or not? Is that true or not? Should we do it again or you like it? That's a different question. Am I missing anything? Is that the most general solution? Plus z
Plus
plus c is not correct.
z. You get one and then 0 later.
That's also not the most general solution. Because this isn't del squared equals the thing again. Right? Because you would have del squared on this side and a z on this side. So it'd be a 0 on one side and a z on the other. So I can't possibly be right. Okay, so here's the most general solution. You need an amplitude. That would be your plus c, right?
Okay.
And you need the other one. Because now when I do two derivatives, I still get back right? Okay. So this is our spatial component with respect to z. That's the general version. So what does phi look like? Oops. Well, it looks like that. Right? So this is beautiful because this now relates this property k, which is the wave number, right, to all of the different components that I care about. It has something to do with the exponential, which is telling us about how this wave propagates down into the medium, right? So remember how this is supposed to look. All right, I'll just do this. Okay, so remember this is how this is supposed to look. Here's 0. Okay. This is minus z, heading towards the bottom. So the question we're asking is not just about the free surface eta, but how does that wave propagate down? Does the wave propagate all the way to the bottom and it looks exactly the same? Or does it change with z height? You see? And now we know from this format is that it must change with z height. And one of two things might be occurring. Either b e to the minus kz. So okay, let's try this one out. Z is going down, so it's negative. So what happens to the b term? B e to the minus kz.
It's quite small.
Well, hold on, think that through. What is the reasoning there?
Divided by. So she figures. That's the one.
Z is negative.
Z is negative, so the argument is
Positive.
positive. E to a positive is do you want your money e to the positive or e to the negative? Go ahead and put it in your calculator on your phone. E to the 10 or e to the minus 10. And then take your account balance and multiply it by that. More positive, right? So what is e to the 10? 22,000. I'll take 22,000 times my current account balance, right? Okay, so let's think about where we started. We started with a little perturbation. We have some like interface of water or whatever with some other fluid, and we create some small perturbation where A is much, much smaller than the wavelength, right? And so we perturb the fluid surface, we create this free surface, and now we have a term here in f of z, something that is describing how it goes down into the fluid, and that's becoming exponentially larger. So what does that tell you about the B term? That's right, it's nonsense. The B term must be nonsense, right? Because if this was the wave and the wave got larger as you went down into it, how could it ever possibly go to zero at the boundary of the flow? Right? Mathematical inconsistencies. So we rely on two things there. One, we have a boundary condition that says at z equals minus h, the thing must go to zero. Right? Or sufficiently close, approximately. And the second part is, it just is a nonsense, doesn't make any sense. Right? As you go away from this wave into the deeper in the water, the wave gets larger. No, that's not physical. What is physical? As you go away from the wave, what happens? It gets small. And that's what this one wants to do. Now it looks confusing because it's KZ, but Z is always going to be negative, right? Because you're going down into the water. So this term is a decaying exponential. But we love those. Those are great for us, right? So we can use our boundary conditions to see which of these two terms are actually helping us. This is a generalized solution for this type of a wave. So for example, if we wanted to go up in the opposite direction, we would use a different set of A and B. But for this specific example, we can say this one's garbage and this one we like. What that means is now as I head away from the free surface down into the fluid, right, there is some area that is perturbed, but it doesn't go all the way down. Decays in strength. So you were saying earlier it's an amplitude. I 100% agree. But it's an amplitude that changes that. Because really this is a series motion. It's a series of waves, right? Or I guess no, I didn't put that up. It's again below. And then somewhere down here. And somewhere down here.
Amplitude is always respect to where your Z is at, right? What's Z?
Yeah, whatever. So if I go down to here, there's one Z and there's another Z. So you can think of them as a series of waves stacked on top of each other. Right? And then by the time that I get way down here, then it like basically looks flat. That wasn't a good job. But this is why I don't draw.
What term is the, I guess, like the thing that is causing it to flatten down?
That's this one here. At every location, let's say we start here, and we just look in Z. I can ask just how it behaves in Z. It's a decaying exponential. So this decays down. This piece here decays down. This piece here decays down. Right? Every single one is decaying. The left-right motion, what it looks like in X, is a sinusoid. That's not surprising. But it looks up down is what we learned today. We love it. So you can get the fluid velocity from this. You can use the boundary conditions. Let me show you one of them. So we can say that look at this piece, right? And we can substitute this into, there's two of these equations earlier. We have this one here, Now we have a second derivative with respect to f. This thing here gives us, where's? I didn't I wrote the other boundary condition. Oh, yes, I did. Did I? So I said at the very bottom, right? W, which is d phi dz must equal at the very bottom 0, right? Okay, so we can use this. This is one of our boundary conditions to find out the relationship between A and B, right? Right. Okay. What is it? W, I'm going to take a derivative only with respect to z. It's going to be 0, so I can drop all of the sign stuff. And I can just take a derivative of this, right? So let's do that. Let's do d dz of f of z. Okay. So what's the derivative? Right.
D A, D K Z.
Why is a z coming out?
Okay.
K,
Okay, my
good,
bad.
good. K, A, E, K, Z. And then minus K, B, E, K, Z, right? And that's minus E, K, Z. And that's equal to? Here. Good. Okay, so this is true at Z equals minus H, right? So let's go ahead and do that. So this will be minus H in here. I'm going to write this as and this one here is now H. Right. You're chilling on that one? And so let's rewrite this. I got K on both sides, so that doesn't matter. I have A and B. So I'm going to go ahead and I'm going to write A e to the minus KH is equal to, I'm going to move it to the other side, B e to the KH. Okay, am I fucked here or what can I do? Excuse me? No, we don't have to do that. It's even easier. What? I want to know A in relationship to B or B in relationship to A. Let's try B in relationship to A. B equals.
We're gonna substitute it once we figure it out.
Yeah, once we get to the end, we'll back to
B equals A over
B equals
A over E to the stuff squared.
E to the minus KH. And if I divide by this on the other side, then I get what? But dividing by something with an exponent is the same as. It's actually not adding, it's subtracting. So let's go ahead and. Okay. So this becomes. Easy breezy, right? Okay, so we use one boundary condition. Okay. Now let's do the other one. What do we know about the I got rid of it already. The very beginning. For the beginning of Monday's class, we said that we were gonna try for solutions of a given form. And in particular, we wanted to talk about how eta had a specific shape. That eta has small amplitude, and it was a cosine, right? Okay, so if we want to use that shape. And we want to write something. Where did we write it? Oh, not,
Start with the pressure.
what?
You talking about the second, boundary of the pressure?
Well, I wanted to look right at the surface. And at the surface, we said something like, del phi over del z. Evaluated at z equals 0. Is going to be equal to del eta del t. You remember that one? Kind of like this one here. We haven't yet described how del or how eta is formed. We said eta should be really of this form, right? We said it should be like eta. We said it should be something like a cos of a x minus omega t. Right? So this side's okay. Right? What do we get there? Negative omega a.
So there's negative.
Hold on. Oh, this is fine, right? You like that? No one upset?
I think the,
Where does the negative sign go?
because we derive the cosine, but then you took the negative from the omega. So then-
Oh, here?
Yeah, when I first figured out.
Oh, yeah, okay, there. Sorry, I misunderstood what you're saying. I thought you wanted to get rid of this negative. Okay, so this one, yeah, that's double negative. So you get one from the fact that it's negative omega, and you get one from the fact that cos became a sine. Okay, what about this left hand side? Have we ever done that before in our whole lives? Yeah, we just did it, right? It's dz df dz, right? Because really we start with d phi, but the only piece that has z in it is this first part here. So we're gonna bring this along because it's not equal to 0 anymore. So we have to do this derivative and then we're gonna times it by this. But it's this thing, right? So it's ka e to the minus kz, right? Except that I put the h in. This one we evaluate at z equals 0. So that's really helpful because then each of these is going to become 1, right? So let's write this down at the top. Okay, so the first part is Ka. The second part is minus Kb. Okay, and then I also have what this is times by, which is sine. Oh my God, look at that. Look at that cash money. So by choosing eta early on, smart, we now don't have sine on one side and cosine on the other. Right? Because look what we can do here. This is sick, right? Boom. Sine's gone. K is outside. So we have something like K A minus B equals omega A. Right? Okay. So you can now rearrange this for A or B. I don't want to do that. It's a lot of work. just gonna look them up. You're gonna get something that's nasty. Okay. You're gonna have a little bit of something in the Z part that is gonna have a cosh and a cinch. It'll be a cosh over a cinch. It's not beautiful, but it's fine. The thing that I really am curious about though, is I want to know the relationship now between these two things. Omega MK. Because this is really something that I'm quite curious about. How does the wave propagate in this media with respect to whether I change H, with respect to how I change A, etc. So I want to know, let's see if I have it here. No, not yet. Okay. Can I get rid of a little bit of this so I can clean some of the stuff up? I'm gonna get rid of this left side. And we're gonna talk about dispersion. Well, yeah, we're still doing something about this. Okay. All right. So, okay, we started off with this equation at the very beginning. We talked about on the right-hand side, we had the Bernoulli equation evaluated at the surface. And we showed that the pressure by definition has to go to 0 at the surface. Is that true? Okay. So what does that say about d phi dt at the surface? Negative g eta. Eta. Good. So now we're very close to what I call the cash dollars. Okay. So we take this derivative with respect to t. Okay. You evaluate it at z equals 0. I'm going to save you a couple steps here. I'm not going to make you do it. Okay. I'm going to give you eta. I'm going to say that this is equal to minus ag cosine kx minus omega t, right? We just did that. That's what eta was. On the left-hand side, you evaluate this whole thing, and it's going to come out to something that looks a little bit like minus a omega squared. Excuse me. Osh. H. Over cinch. H. Cosine x. And this we love, because again, we take advantage of the fact that we were so smart, so clever, we thought ahead of time. We can get rid of these coses, right? We don't care about them. The A's really don't matter here, right? And instead I have a relationship now between omega and k with respect to g. Only thing that matters on this side is minus g. So the minus, of course, we can get rid of those two. So I really have something that looks like omega squared over k, right? Osh over cinch equals g. Right? What?
You cross out the A on top of the.
Yeah, this is an omega square. It's the same shape. Sorry, it does look like an A, I guess. Let's do this. Is that better? Okay. Okay. Cos over sine. Inverse tan is the arctan, right? It's 1 over the tan. It's 1 over the tan.
I thought it was an angle.
It does have. But I don't think it's inverse tan, I think it's cotangent, right? COT.
Yeah.
Okay, so this would be COTH. But I really want to understand something different here. I would like to know the relationship between W and everything else in this problem. So I'm gonna go ahead, I'm gonna flip that over, consolidate it into tan. Okay, let's do that, that becomes tan. Okay, I'm gonna put the K over there. And I'm gonna take the square root. Okay, so let's write that again. W equals square root of K G tan. Oops, fuck. Tan K. Okay. So now I have what are called a dispersion relationship. How does the angular frequency change as a function of the wave number? We said early on that this choice here, kx and omega t, that they were married. They're friends with one another. And now we have the relationship. This is not two independent quantities for the wave. By definition, in order for the wave equation to work, they have to be coupled, and this is the way in which they are coupled. Okay? This might not make a lot of sense to you yet, but that's because we don't have an intuitive understanding of tangents, or at least I don't think you do. You guys? So let's look at some examples really quickly. The phase speed. This is it. The phase speed is the thing that we know as c in a fluid. And c is equal to omega divided by k. Like this. Omega divided by k. I get what? G over K. Good. G over K. And KH. Okay, or I can also write this in terms of K. What was K in terms of lambda? Remember? Pi over lambda, right? So now I can write something like this. G lambda over 2 pi and K. Okay, now we really have understanding here. What do I mean by that? We tend to think about waves. I mean, so you could obviously talk about omega, and omega would be something like the angular frequency of the wave. And you have an intuitive understanding of that, because that's like how quickly does it go by you, right? But you might also think of this in a more physical sense. You might think about it like, what's the wave speed? How do the waves disperse? Hence the word dispersion relation, right? So do they propagate at the same speed as they move through the medium? Do they slow down? What happens to their amplitude? All those types of things, right? Okay. So let's have a look here. C, G, so G is probably not changing in the book, right? What about lambda? Lambda can change, right? We can make any sort of perturbation we want in this fluid. And let's drop a big rock into this fluid, and we're going to start some waves. And let's start a bunch of different waves from very small wavelength to very large wavelength. Now let's look very, very far away. What do you see? Out of the surface. You gotta wait. Okay, take your time around. Okay. So Metzley's over at that part of the water. I'm at this part of the water. She drops a big old rock, bunch of waves form there. They're headed towards me. I have my little stopwatch. Who gets to me first? Yeah, who? Which waves?
The first ripple.
No, well, read off the board. What does it say? We just found something. Let's use it. It is true that intuitively we should have these answers. That's not what I'm asking. I'm trying to see if that explains our intuition. Did we just write garbage on the board, or is it useful? What is the first wave that gets to us?
It's just a wave that.
Sorry, say that again.
The largest one.
The biggest lambda has the highest speed. The smaller lambdas, they don't have very big speed. They may never get to us. Right? So your idea of the first one is right, but now we have the word for it. That big perturbation moves out the fastest. And everything else trails it. This is how the velocity is dispersed over the wavelengths. Remember that waves do not interact with one another. They pass through one another harmlessly. You have some short wavelength like this, and a big one passes right through it, and it doesn't change this one. Right? They add together for a little while, they look really cool, and then they go back to being not friends. Right? And of course, this describes the vertical depth, but if h is very big, you can see what happens to the tangent kh.
Since this is just the speed, where do we, so I think of dispersion, I'm thinking from like a point and then like radially outward. When do you have direction? It's like. Is that at least radially outward from a point?
Okay, so you're thinking a different way of the word, a different way that I would interpret the word dispersion. Dispersion. You're thinking in 3D. We're not in 3D. We've never even heard of 3D. Right? We're just thinking about radiating from x to minus x.
Yeah.
Because you can't radiate even in z. Right? That just goes up and down. Free surface up and down, up and down. Right? And so I drew this really great picture. Right? Sorry, this is very complicated. Right? And that's sub lambda. And there might be smaller lambdas or bigger lambdas. And they might emanate from this region, going off left or right, depending on bits, right? Kx minus omega t. That's going to send them in different directions. And the speed at which they go is called the phase speed. Okay. How does blue particle move? Yeah. Describe the life of a fluid particle here in this object.
Causes it to,
Excuse me?
other things cause it to.
Okay, what I mean by that is think about what, like, let's say you are a streamline or who's the one where it goes through the path of the particle itself, the straight line of the particle? Let's say you are a little droplet of fluid here. Now what? Good. Where does it go? There's a little droplet of fluid right here. Where is it going? Okay, so you go like this. I'll probably make this and I'll probably regret doing this, but we're gonna do it anyway. I just need like 4 boards, that's my major problem, okay. The particle here. That's what you say. And then what?
Follows the weight.
Goes like this. And then it goes like this. And then it goes like this. And then it goes like this. Okay, let's say I'm a bird. This is a bird, okay? Just relax. Okay, that's a bird. Okay, relax. That little tune out of the water. Where does the bird go? This way? And then this way? Then this way? And then this way? We in trouble yet? Oh, sorry, excuse me?
Great, but then let's go up and down. It just sits there.
You're saying it goes to the left? You're saying it sits there? Now we have real contentious. Now we're gonna need to go to the beach for show. Determine how the bird move. Okay, so the bird you claim goes up and down. That's your claim?
I wanna say because of the surface, they don't move.
But you just said these move.
But those are not at the surface.
Okay. And you claim that it goes to the left. Actually, it's an optical illusion. And it goes that way. Is that your claim? And your claim? You like vertical, so how many vertical?
We always have a string.
Oh, buoys have a string, oh shit, but is that to move them left or right?
I think that's supposed to keep it, so it just moves up and down. So it doesn't move much.
String doesn't, just controls it staying above the thing that's dangerous, right? I don't think a buoy is a good choice here. I wanna know, how does the thing move in the water? Okay, I got my bird is my tester bird. Okay. I got some votes for up, down. I got some votes for left, right. Okay. What?
Pushes you, lazy river pushes.
Well, that's because you're submerged, so parts of
No,
yours.
wait, so the things on the top.
Okay. So surface waves, do not cause fluid elements to travel. This is wrong. Bird does go up and down, but it goes up and down weirdly. Let me show you. This is the motion of a bird. Almost, it means that we have a smaller one here, and a smaller one here, and a smaller one here. And over here, let's say it's going this direction. Over here, it goes in the other direction. Okay.
You're talking about when you bend that line, tilting, it falls. Vorticity?
Excuse me?
When you're talking about how you cause vorticity when you bend the line. Is that what that side function they're doing?
Well, what we're thinking about here is just the way that the motion is propagating down into the fluid. And what we found originally is that you have some propagating object to the right, and then it descends into the fluid where it becomes less important. Right? Now this is exaggerated. These things wouldn't go down to this far, right? And we said that as they descend, they're changing their shape. So this is the exponential decay. You can see that it's kind of curved like that, right? But the motion is still sinusoidal. The only thing is that the particles don't then leave their, so this thing is gonna go float, 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 float. In order for it to do that, you have to go up and then down, and then up and then down. You see, so the whole thing goes flip, flop, and it doesn't look left, right, because the fluid here doesn't know that it's moving. It only appears to move. So similarly, the bird goes flop, 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 flop. but he rides on the surface. So he goes flop, whoop, flop. So the bird does move back, forth, and up there. It's a little complicated.
So it's kind of like how electricity is going in the wires, like an AC, they just have it like that, then like direct current, it would have been like how we were thinking the particle would keep on traveling through the wire. So that's kind of,
Yes, yeah, okay, that's a very good analogy, right? So you have some, like, instead of an electron moving from one end to the other, it's really just moving its friend nearby.
Yeah.
Right, and similar to what we're thinking about is as this guy pulls down on the fluid, it pulls down on this fluid. And so we have these two cogs that turn into each other, right? Pulling fluid down, and then since this one is rotating, it must necessarily rotate the other one. Right? But like cogs, or like, you know, the kids who play with those ones that you enter and you create a whole bunch of them. That's what we're doing. Cool beans?
In the case of the bird, is the fluid moving the bird?
What do you mean by that?
Like, is the motion of the, like, of the wave, is the wave itself moving the bird? Cause you're saying it does like a little, like square, I guess, or a circle, is the fluid what causes the bird to move?
Yeah, so you're sitting, we sit a bird up here, right?
Yeah,
So the first thing that happens is these particles are not moving like from here to here.
Mhm.
They're going like this, and then they're going like this, and then this, and then this, right? So even the ones on the top there, they're going like this, and then this thing starts to drop down, and so they come back. So the bird flows across, and then over, and then across, and then over.
so what would move the bird is like the wind on top of the water.
Right, yeah,
Okay.
or you probably don't see it's that little. But if it's really just sitting there chilling, like a boat, the boats just bob up and down from our perspective, right? The waves go by and they just go. And your buoy example is great, right? But it is tied to the ground. So it both is restricted from just going up and down like this forever and also from the trend is danger. Okay. So here's what they look like. You can do the path line. I might do this as a homework problem, just if you don't have time for it here. This would be the path line of any particle, and they're gonna make ellipses. Based on our equation. Okay. And then the important part here is that you will end up with something with streamlines, and you'll have some different equations, basically based on how deep the waves are compared to so this piece here is what I care about. Lambda's relationship to tan H. How deep is the flow? So something like this, where we can consider it very, very deep, is that picture that I drew before, and these circles sort of gradually get smaller quite quickly. Something where lambda and KH are more comparable to one another, that is to say the perturbation of the wave size with respect to the depth is in the intermediate range. These ellipses, they're going to be more flattened. They're going to be, so these are more circular, these are more flattened, right? And you have much more of this back and forth motion before you go up and down. So here the particles are really feeling like they're moving back and forth. They're still in ellipses. Okay. And in the shallow version, we'll spend a lot of time here in shallow waves, or at least one class. That's a lot of time for some folks. Okay. These, notice that they're not really decreasing that rapidly, right? Because I can still get away with the boundary condition of not going through the surface if all my velocity is left right.
That's what we started with the other day, right, last week, because we said A over lambda. The comparison is very small, less than one.
A over lambda.
We wanted the length to be much greater than that.
If we want the length to be much greater than the height, then we want deep. All right, because this is small compared to how deep the water is. These disappear. We haven't done shallow waterways yet. We've done deep waterways. That's like where we start. Deep waterways are the easiest. Because then you're really not interfacing with the deep as much.
I don't understand why the circles of the deep are not the same in shallow, except smaller. Like I would think that the circles, because of deep, the same circle should be in shallow, except smaller circles, maybe the gap might be smaller.
Well, look at one thing that's happening in each one of these three pictures, right? In this picture, the size of the perturbation compared to the depth, right, is what I care about. Here, the wavelength is larger compared to the depth. Here, the wavelength is actually comparable to the depth. Right?
If I have a wavelength the same
So if you have this
That way,
length
in
here,
shallow,
then it might not be shallow. Right? Because the definition of shallow is not how deep the water is. It's how long the wavelength is in respect to the depth of the water. So we might consider something deep to us. Oh my God, that's 10 kilometers deep. That's so deep. But if the wavelength is 100 kilometers, then it's certainly shallow. Right? So again, we're kind of going back to this idea that fluids are quite difficult to just one size fits all, because we made a bunch of approximations in order to do even this, right? In order to make this simple wave dispersion, which by the way, not so simple, but you know, the easiest one we could come up with, the first one I wanted to show you, we had to assume things like we're in deep water. We had to assume things like the A is much, much less than the wavelength. That is to say, the actual height of the wave can't be big compared to the wavelength. Right? Small perturbation. Is that going to generally describe all the fluids we see? No, not even the most minimal ones. Right? The waves that you see at the beach, they're not this. I made you use some intuition that was close, but not exactly, right? The waves that you see at the beach are much more like this, because they're crashing into the water. And there's certainly A is much larger than right there, like breaking and everything else. Okay, we can do streamlines of the flow. That's what they look like. I think this is stuff that you probably will want to do by yourself, if you want to. Because I think the next thing that we're going to do is we're going to do approximations for deep and shallow water. We're going to simplify it even further. The deepest one, deep is easy. Okay. So I would like you to ask the question. We have this phase speed, just while we have it up. What is tanh of x when x is small? But do like tanh of 1. Tanh of 1. Tanh of 0.1. 0.0. Correct? So if I said something like tanh of x approximately equal to
If you have big X's, it goes to one.
What?
If you have big X's, it goes to one.
Okay, that's not what I asked, just for small x. Nope, or no, tangent of x is approximately equal to. X. That's the small tangent approximation. Okay. So if kx. If kh is much, much less than one. Then what do I got? Boom, bada bing, bada boom. And that's awesome, because then C is the square root of G over K times KH, which is H. Let's fucking go. What have I done?
If the approximation that page is very small.
We can skip all the tangent stuff and just say that the phase speed is the square root of the height, or the depth and the gravity.
Yeah, so gravity's not really changing, right?
Yeah.
But the height is what matters. Right? So this is a simplification for deep water. Okay. So deep is by definition, we're going to call deep H is bigger than lambda. And lambda is 1 over K, essentially. So it's HA. Write that down. This is why you don't do it right at the end. Okay. Oh, no, I did this backwards. This is shallow water. We'll do deep in a second. So deep is much bigger. H is much bigger than lambda. Shallow is H over lambda, much less than 1. And H over lambda is H. Okay. Questions, comments, concerns? For deep, by the way, what is tangent of x as x goes towards infinity? What was that? 1. So that makes it even easier too, right? Then C is equal to okay. Simple. But here's deep. Here's shallow. Cash money? Questions, comments, concerns? Yeah.
What changes a non-zero exponential?
The depth of those rotating things. So it's going to be the f of z that we talked about at the beginning. It's going to be exponential kz and then minus k. Yeah, those terms, once you solve for a and b, they become coches and cinches. And those koshas or cinches, you know, they're combinations of exponentials, positives and negative exponentials of the same type. So they're just slightly easier to write with koshas and cinches because it's the same thing divided by the same thing. But yeah, they're essentially plus minuses, those exponentials. Deep or shallow? Deep? Look what he's doing. It's called the surf. Let's draw the surfer man. Why does it do this? Counterintuitively, it's because the ground is doing this. So it's unfortunate because what you can't see in the picture is that this pileup here is what makes this break. So waves like this, especially these massive ones, think about them as being deep. They're coming from the deep ocean, but they're very quickly becoming shallow. And that's why they break. Because the very top is moving quite quick. We'll talk about the dispersion relationship here, right? C, notice this one, only depends on H. This is for shallow. Now everything's moving at the same speed. This is speed. They depend on wavelength. And in particular, right? This one is G lambda over 2 pi. What's moving the fastest? Biggest. So you start with some big perturbation, right? And they're moving, and all of a sudden they hit. And now they're all moving at the same speed. They're trying to move all the same speed. With this big guy, he's moving the fastest, falls over. Right? That's wave breaking. Okay, sorry, I kept you guys a bunch late. Fun. It's sick. Oh.